Okay, we have here today another interesting integral. This one was sent to me by Sid. We have the integral from 0 to inverse cosh of square root of 2, natural log cosh of x, hyperbolic cotangent of x dx. Okay, I might do two videos on this one, but for right now, I want to kind of do this out using a u substitution. So what's going to happen here, I'm going to want to try to simplify it this way. Part of the thinking on this is it's going to work well with the bounds here. So if I do u equal to cosh of x, then instead of taking the derivative, let's take the inverse before taking the derivative. So we can write it as x as just equal to inverse cosh of u. Then take a derivative. The derivative of inverse cosh is going to be 1 over square root u squared minus 1 du. Then one other thing before we substitute, hyperbolic cotangent. So breaking this up, hyperbolic cotangent, this is going to be the same thing as cosh x over sinh of x. Now we already have our value for cosh, that's going to be u. So we have u over sinh of x. For this, I want to use an identity. We have that sinh squared of x is going to be the same thing as cosh squared of x minus 1. So if I just take the square root on both sides, then what we end up with is going to be sinh x equals this thing, but again, cosh is u, so we can write this as square root u squared minus 1. So in our value for hyperbolic cotangent, let's plug this in, and I can write this thing as u over square root u squared minus 1. Okay, so now I think we have everything we need to do this. First, we can go ahead and update the bounds. When we plug this inverse cosh square root of 2 into here, cosh of the inverse, it's just going to give back square root of 2. You do need to be a little careful, but it works here when we have positive values. If it was negative values, sometimes you get in the situation where you get the negative value, but here it works. And then plugging in 0, cosh at 0 is going to be 1. So then we'll go ahead and substitute. First, this is going to become ln of just u. Hyperbolic cotangent, we got our value. That's going to be, I'll just kind of rearrange it. Let's bring the u over here, write it all over u squared minus 1. Our dx value is this thing, another copy of square root u squared minus 1. But of course, I can multiply these together and combine them. When I do that, let's kind of combine a step here. For u squared minus 1, I can factor that as u plus 1 times u minus 1. And with that, it's going to motivate me to rewrite this u, because I want to get cancellation. So how we're going to do this to try to clean it up, just to avoid any kind of partial fractions or any kind of long algebra, we can do this on the fly. If I take u plus 1 and add it, we don't want to subtract it because we lose our u. So if we add u minus 1, then the 1's cancel. That's nice. We get back 2u, but we want just 1u. So all I need to do, let's multiply by 1/2 in front here. And that way 1/2 times 2u is still u. We haven't changed it. And with that, we can now break this up into two integrals, breaking it on this plus sign right here. So we have the integral going from 1 square root of 2. The first one's going to be this u plus 1. And then for the second one, distribute in the 1/2. And now we're just going to have the u minus 1 on this one. But then we can cancel out u plus 1 here, cancel u minus 1 here. We're definitely not done yet, but we do have two integrals now that we can deal with. Let me clean up the board and we'll continue with this. Okay, now on the rewrite, I did one sneaky maneuver. I took a minus sign out from the denominator and reversed the sign here. This was u minus 1. I did that because I wanted to use the formula for the Dilogarithm. If we look at this right here, this is going to be in exactly the right form. We have the lower bound at 1 the way we need it. This is going to be our input. So this thing, using the formula, this is going to be Dilogarithm of just 1 minus square root of 2. Hopefully we can get a nicer value for that later, but for now let's just bring down the minus 1/2 in front, and we'll kind of put this one aside because this is about as good as we can do right now. On this second one, because we have a plus sign right here, it's not quite in the same form. Even if we kind of create a minus sign right now, I don't think it quite works because then we end up with a minus sign. We can do a substitution, but it doesn't quite work for the Dilogarithm yet. So what I want to do is let's do integration by parts using the DI method over here. We'll just differentiate natural log u because that's what we like to do. And we can definitely integrate this thing. So when we do this, we differentiate, we get 1 over u. Integral here, ln Drop the absolute value because we're always positive here, so we just leave it as natural log 1 plus u. Then we have part of the solution on the diagonals here. This is going to be 1/2 natural log u, natural log 1 plus u. But we're going to need to evaluate it here from 1 to square root of 2, running out of space. And then the last row is going to be an integral. I'll distribute on the 1/2, so we're going to have minus 1/2, and this is going to be natural log 1 plus u over u from 1 to square root of 2. But this is actually an improvement. It might not look like it, but we're getting somewhere. I can take this minus and bring it inside here and make this a minus u. And then I can manipulate this a little bit for plus u. This is kind of like when we're trying to set up like the geometric series formula. We can write it like minus u. And then that's going to motivate my substitution here to try to get this one into the form of the dilogarithm. So what I can do is I can do t minus u, very simple one, just changing the sign, right? So we do dt minus du, and then we can substitute on this. So let me just focus on the integral for the moment. We'll plug it all back in after it. I just don't want to keep rewriting everything. So when we do this, we're going to reverse the sign on the bound. So now it's going to be minus square root of 2, minus 1 at the bottom. Then we're going to have natural log 1 minus t over t. The dt value, or du is going to be minus dt, right? We could just rearrange it like that. So this is going to be dt minus in front. Now this is very close to our formula. The only problem is we want this to be a 0 here. What I'm going to do is force this to happen, turn this into a 0, and then it doesn't matter that it's a negative sign. We can just use the principle we use adding and subtracting integrals that we always use. Be like we're subtracting, but we have a minus, so the minus will become a plus, and I can write this as now the same integral going from 0 to 1 now, and we're just kind of like subtracting off that area. And sorry, this was supposed to be a minus 1 right here. And so now we can use our formula for the dilogarithm. Let me just label these. So this one right here, because the input, we got the minus sign in front, so we're perfectly set up, and our input on it is just this minus square root of 2. So this one is going to be dilogarithm minus square root of 2. This one over here, we don't have the minus sign, but you can create it. We can just turn it into you could do it like minus like that if you want. And so for this one, the value of this is just going to be dilogarithm, input here, minus 1. So now you can see I have a mess, but we can put it all back together because let me just summarize all the different things we have. We've got this piece from the beginning. We've got this that we still need to evaluate, and we've got 2 dilogarithm values. So I'm going to clean up the board. We'll bring it all together, evaluate it, and see if we can finish it. Okay, now we can just see if we can try to evaluate this and put it all together. Let's kind of regroup things a little bit. So we've got 1/2 everywhere. Let's take this piece and this piece here and put it together. So we'll have 1/2 dilogarithm minus square root of 2 minus this one. Now for dilogarithm minus 1 right here, I showed the value. We did this out in another video. I'll provide a link in the description to the playlist on the dilogarithm as I derived all the values. So we derived this in another video, and it was minus pi squared over 12. So because we've got a minus in front, I can write this in as pi squared over 12, positive pi squared over 12. Then we can evaluate this. When we plug in square root of 2, we get natural log square root of 2, natural log 1 plus square root of 2. And one mistake I noticed, I need to distribute this 1/2 into the pi squared over 12, so this becomes pi squared over 24 when I do that. And I'm skipping one thing. I'm skipping the evaluation of 1. It's just because when you plug in 1 here, natural log 1, 0, the whole thing gets zeroed out. And now we're getting close, but we would like to have a value for this. I'd rather not just leave it in terms of the dilogarithm. Sometimes you have to because there's a lot of values you can't find. These are not, I don't think there's a nice value for this, so I don't know, I can't tell you exactly what dilogarithm of minus square root of 2 is. But the good news is we've got an identity for this thing, so let's look at our identity that we can use to simplify this. Okay, now here's the formula I want to use on this. It is kind of troubling, right? Because when we do it, we simplify it, but then we just get another term with the dilogarithm. This happens a lot with the dilogarithm. You try to simplify it and you just get another dilogarithm. But let's just do it and see how it goes. So our x value on this is going to be square root of 2 to just plug in everywhere. And notice if this is our x, it's going to match both terms. We get minus square root of 2, and then here 1 minus square root of 2. This is going to work. So plugging into the formula on the right side, we get minus pi squared over 12 plus natural log square root of 2, natural log 1 plus square root of 2 plus 1/2. Okay, and here's the important part. 1 minus x squared is going to be 2. So we have 1 minus 2 here. But 1 minus 2, that's going to be a minus 1. And that's the thing we just found. Or that's the thing we found in another video, but we just did it. So this is actually minus pi squared over 12. So let's see, when we multiply 1/2 times minus pi squared over 12, this is going to become minus pi squared over 24. I can turn this one into 2 pi squared over 24. So when we put this together and this together, we get pi squared over 24, but I want to distribute in the minus sign. And so what we have on this is going to be minus pi squared over 24 plus, or sorry, distribute the minus, and this should be a negative. So we have minus natural log square root of 2, natural log 1 plus square root of 2. Okay, so all I need to do is we need to take this and throw it back in for this red piece right here. And then when we distribute in the 1/2, just notice what happens. This is the same as this. We're going to end up with minus 1/2 here, plus 1/2 here. This is going to just cancel out with this. And then we just have to put together these pi squared terms. So we have pi squared over 24 using this one. Distributed in the 1/2 here, we've got minus 1 over pi squared over 48. Multiply in 2 over 2 here. This here is going to be just 2 pi squared over 48 minus pi squared over 48. And for my final solution on this, we just get pi squared over 48, and that's it. Okay, so there you go. Really like this one a lot. Thanks again to Sid for the problem. Thanks everyone for watching. Have a good day.